Hello, ChemComm. At this point in Unit 6, we've talked a little bit about the history of nuclear chemistry. Now we're going to dive deeper into what nuclear chemistry is and the different types of radiation that we see emitted from the nucleus of an atom. Let's get started. A question I like to ask at the beginning of this section is, where does your mind go when we start talking about nuclear chemistry or nuclear radiation? A lot of people think about the little boy and the fat man that we dropped on Japan during World War II to end the war. Those nuclear weapons had uranium and plutonium as the radioactive isotope. These were some of the more profound and somber uses of nuclear radiation. You might also think of the Chernobyl reactor in the Ukraine that in 1986 melted down, which has made Chernobyl inhabitable up until recently. You might also think about things like nuclear power and how we're trying to switch to clean energy. And you may have heard nuclear talked about as clean, but you know that there's nuclear waste and have questions about that. Today what we're going to try to get into is the nuts and bolts of what nuclear reactions are, and then that'll help us understand why they can be dangerous, but also what they can be used for. As we said before, nuclear chemistry is the study of any change within the nucleus. That could be adding two nuclei together or breaking a nuclei apart into smaller pieces. Typically, it's breaking nuclei apart into smaller pieces. Let's go through a couple ways that can happen. There are three types of radiation that you need to know about. The first one being alpha. And all of these, it's when you have a nucleus that is unstable because of an imbalance in protons and neutrons, which are both in the nucleus. And because of that instability, a piece will break off of the nucleus, a part of the nucleus, a certain amount of protons and neutrons. The first particle that could break off of a nucleus is called an alpha particle. We can see the alpha symbol here, and what this tells us is that an alpha particle is really just a helium nucleus, which is 2 protons and 2 neutrons. So if you think about it, the positive charge would be 2, and because we have 2 protons and 2 neutrons, the mass would be 4. A lot of times you will see this written like this, because it has a mass of 4 and a positive charge of 2. So after that alpha particle breaks off, that leaves a different nucleus. And part of what we're going to be doing in this section is figuring out what part is left. The second type of nuclear radiation that we can talk about is a beta particle. So a beta particle being emitted or breaking off of a large unstable nucleus. A beta particle is basically an electron. You can see here the symbol for the beta particle. And you can see that it has a charge of -1 and negligible mass. So a lot of times we'll write the beta particle with a mass of 0. We'll put E for an electron and then a -1. You could also write it like this with the beta symbol. Both of those would be okay. You'll notice that because this particle is smaller than an alpha particle, it has a greater ability to penetrate, meaning it can go through things easier. The last type of radiation you need to know is gamma radiation. Gamma radiation is not a particle. You know that on the electromagnetic spectrum, we have gamma radiation, which is a high frequency wave that is very dangerous. That's exactly what this is. A lot of times the way we represent this is just by drawing a wave to show that it's not a particle. Because it's a wave and it doesn't have mass, this has very high penetrating ability and ionization ability. This can travel through lots of things like walls and even thin concrete. This is why when we have nuclear fallout, you'll see people in those radiation chutes that are laced in lead so that the radiation, the gamma rays, can't get through the suit. You can see here a little bit what we've talked about. Here's our alpha particle, 2 protons, 2 neutrons. It's a large particle. It won't even travel through paper. Then we have our beta particle, which is a mass of 0 because it's so small. And it'll go through paper, but it won't go through like an aluminum plate. Where gamma radiation, because it's a wave, it can travel through much more, and that makes it more dangerous as well. Here's another thing that helps us understand the particles. We have a negative plate here and a positive plate here that's creating an electric field. If we emit these different particles out of this radioactive sample, we'll notice that the alpha particles bend toward the negative plate because they're positive. We'll notice the beta particles, because they're negative, bend toward the positive plate. And we'll notice the gamma rays don't move at all because they're not a particle with a charge. Notice also that the beta particles move more. They bend more. Why? Because they have less mass. Less mass means it's easier to change their momentum and therefore to be more affected by the electric field. If we're going to have these types of decay, we're going to have to talk about radioisotopes. Radioisotopes are basically any isotope on the periodic table that has a large enough nucleus and a correct balance of protons and neutrons that it's unstable, and therefore it would spontaneously decay or spontaneously emit one of these particles. Everything above number 83 on the periodic table is radioactive and therefore don't have stable isotopes. When it goes through this decay, we often call it a transmutation. A transmutation is when a particle of a nucleus breaks off and then it becomes some different element. These transmutations can happen over and over again until we get down to a stable isotope, and we call this a radio decay series. So uranium-238, which has 92 protons, will decay and keep losing particles all the way until it gets down to lead-206. Lead has 82 protons. That's multiple transmutations that it has to go through to get to lead-206, and we call those multiple transmutations a radio decay series. A big part of this section is knowing how to do alpha and beta emissions and write them out in an equation. These aren't difficult, the math is simple, but they do look kind of hectic when you look at them for the first time. So let's walk through them slowly. In this first example, we have uranium-238 that decays by alpha emission to produce thorium-234. So the first thing we want to do is write the nuclide for uranium-238. So we know the mass is 238, and if we look at the periodic table, we can see that it has a positive charge of 92, or 92 protons. Then it says that it is emitting an alpha particle. What that means is that this nucleus is decaying and producing an alpha particle. You can put an alpha particle with the alpha symbol, or you can use He for helium. Both of those are okay. And you have to remember that an alpha particle has a mass of 4 and a positive charge of 2. Then it says we produce thorium-234. If you look at the periodic table, you'll see that thorium has a positive charge of 90. So there's a couple things here you need to take a look at. First of all, we are balanced not only with our mass, but also with our positive charge. So here's our dividing line right here. Here's our equal sign of the equation. If you look at the mass on this side, the total mass, we have 238. And if you look at the total mass on the right side, guess what? 4 plus 234 is 238. Also, if we look at the positive charge on this side is 92, and if we add the positive charge up on this side, we get 92. Since mass and atomic number have to be balanced on both sides, we can use this to solve more complex problems that are nuclear decays. So this problem says thorium-234 is also unstable and will go through beta particle emission. So first we'll write down our thorium-234 nucleus, and it's going to emit a beta particle. So that means it's going to produce a beta particle. And if you remember, a beta particle has a mass that's negligible, or 0, and a -1 charge. And so what it wants us to do now is figure out what's that other particle that's going to be left. Well, we have a mass of 234 on the left, so that means we need a mass of 234 on the right. And since this is 0, this particle will have a mass of 234. On the bottom here, we have a mass of 90 on the left, and then now we have a -1 on the beta particle. So the question is, what does this need to be so that it adds up to 90, like on the left side? And the answer would be 91, because 91 plus -1 equals 90. And now all we have to do is identify the atom that has 91 proton. If we look at the periodic table, we see it's Pa, or protactinium. And that's how you'd write a nuclear equation when you don't have all the information given to you. So those are two different transmutations, one of an alpha particle, one of a beta particle, and those transmutations keep happening until you get to lead-206, which would be a stable isotope. And we call those multiple transmutations a radioactive decay series. That radioactive decay series looks like this. Lots of alpha and beta emissions to get to lead-206. As we just showed you, the law of nuclear equations is the charge needs to be balanced on both sides of the equation, as well as the mass needs to be balanced on both sides of the equation. Now that we've shown you those equations, let's spend a little time talking about some applications for nuclear chemistry. The first thing you need to understand is nuclear fission. Nuclear fission is when nuclei break apart into smaller pieces. Emitting an alpha particle or a beta particle would be a type of nuclear fission. Another way to make this happen is to bombard a nucleus with another particle to make it unstable so that it will break apart. We call this induced radioactivity. Once it decays with one atom, that could likely start a chain reaction. and you need enough atoms for that chain reaction to occur. The amount of a substance, or the amount of a radioactive substance that you need to get that chain reaction going, is called the critical mass. That chain reaction could look something like this. And you can see with every one of those splits, energy is being released, and you can see how that could become dangerous if the reaction happened too fast. So a fast reaction is what you want if you're making a weapon, but if you're doing something like nuclear energy, you want that reaction to be slower. So this is kind of a simple drawing of a nuclear reactor. And what you have here is you have your uranium fuel that's decaying over time, and it's generating a bunch of heat. And what you want is you want that heat to be displaced into something. And so typically we displace it in the water, which generates steam, which turns a turbine. That's why all nuclear power plants, they're near large bodies of water, because they pump water in from a local river or lake so that they can cool down the reaction and keep it from going too fast. Nuclear fallout, or a nuclear meltdown, is when that system breaks apart and therefore the reaction happens too fast in an uncontrolled way. Nuclear fusion is when you have two nuclei and you fuse them together. This is much more difficult than nuclear fission and takes a lot of energy. The pros, though, are if you can get the fusion to start occurring, it's going to generate a bunch of energy. This is what's happening in our sun. Our sun is fusing together hydrogen nuclei to make helium nuclei, and it produces a lot of energy that we benefit from. So what can we use these radioisotopes for? One way we can use them is medical tracers. We can put small, low doses of radioisotopes in your body, and then we can trace their pattern and how they flow through an organism. It might help doctors identify a problem in one of your body systems. We also use gamma radiation to fight bacteria, and even in chemotherapy to destroy cancer cells. Another thing that scientists do is radioactive dating, where they look at radioisotopes that decay over time, and they use it to backdate it to when it would have first started to decay. One type of radioactive dating is using carbon-14 and how much carbon-14 is left in old organisms' bones and tissues. Another way that we've used radioactive isotopes recently is with particle accelerators. We bombard atoms together and we try to fuse them together and create stable new elements. This is how we got to element 118. We've named elements in your lifetime because of massive particle accelerators. This is literally just a tunnel where we shoot beams of electrons and beams of other particles really, really fast in a circle, and then we collide them together. To get an idea of the scale of this tunnel, if you look right here, you'll see a person. This is a massive construction. And finally, we use nuclear radiation for energy. We have lots of nuclear power plants in the United States, and we're getting more. There is a push toward more clean energy, and nuclear chemistry is pretty clean, but it does produce waste that we have to figure out things to do with to allow it to decay over time. Here's some more pictures of particle accelerators and the scientists and engineers that work on those systems. There's lots of high-level science and engineering that goes into these particle accelerators. I hope that it gives you a little background into nuclear chemistry. It really just scratches the surface in all the different things in our society that we use nuclear chemistry and radioisotopes to do for us. Make sure you practice those nuclear equations and the decay of alpha and beta particles. Next time we'll talk about half-life. We'll see you soon.